Hello everyone, bonjour à tous. Welcome to the online seminar series on programming in mathematics education. I am Chantal Buteau from Brock University, and I'm delighted to be co-hosting this event with George Gedenadis from Western University, and with the help of Ariel Figov from Mathematics Knowledge Network and Sarah Gannon, a graduate student from Brock University, and we're all in Canada. We wish to begin this event by acknowledging this land where the Fields Institute for Research in Mathematical Sciences is situated, and from where we are hosting this online event. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to be hosting our online seminar series from this land. So this is a seminar series that we decided to launch this summer in response to the pandemic situation, as many scholarly events were being canceled or postponed, such as the ICME 2020 in Shanghai, China. We decided to fight the confinement and instead meet and discuss online. And so the aim of this seminar series is to provide a platform to discuss recent research on the integration and use of programming, or more broadly, computational thinking in mathematics programs. And such discussion of the research addressing different topics such as student learning, so related student learning, the interplay between affordances of computational thinking and mathematics, the nature of exemplary tasks, pedagogical models, instructional materials and resources, assessment practices, etc. Now, with this in mind, we are delighted with the group of experts who have accepted our invitation to be part of our seminar program for the summer, and who will undoubtedly engage us with insights into programming in math programs. So to launch this seminar series today, we will hear Celia Hoyles and Richard Noss from University College London in the UK. On July 3rd, we will hear Krista Francis and Brent Davis from University of Calgary, Canada. July 17 will be Michelle Wilkerson from University of California, Berkeley in the US. July 31st will be Kronis Kinigos from University of Athens in Greece. Mid-August, August 14, will be my co-host, George Gedenadis from Western University. And we will end and close this seminar series on August 28 with Paul Drivers from Utrecht University in the Netherlands. We have informed our speakers that we were aiming at the demographics of about half academics, a quarter students, graduate and undergraduate students, and about a quarter elementary and secondary school teachers and leaders, and which turns out to be pretty close to the registration that we have received, in fact. And also, due to the online format, we were aiming at potentially reaching demographics beyond the Canadian borders. And as you can see here, having received registration from 24 different countries, we can say that has been successful in that regards. These seminars are all being recorded, and they will be available for free on the Math Knowledge Network website. And you have the link here. It's the same link as was sent on the poster to advertise the seminar series. Except for today, because we are introducing the seminar series, all of the remaining seminars will be of 75 minutes long, 75 minutes duration, and they will all have a similar format. So basically a short introduction of the speakers, and then about 45 minutes seminar presentation. That will be followed by a moderated question period. For that part, we will first open questions from the guest speakers that are attending the seminars. They may wish then to enable their camera when they ask the question, so everyone sees them if they wish when they ask the question. That will be followed by questions from every attendee to this seminar. For this, right now, you cannot, your microphones have been locked and your cameras. So if you want to ask a question at that time, you will need to find the hand icon, and you will need to click on the hand icon to raise your hand to indicate that you will want to ask a question. On our side, then we will unlock your individual microphone, and importantly, you will have to yourself unmute your microphone when you ask the question, okay? We might help you if needed when the time comes. And basically then after that, we'll just very briefly say thank you and say goodbye to next time, until next time. So that's basically the structure of these seminars all the way to the end. We want to thank the Mathematics Knowledge Network, hosted at the Fields Institute for Research in Mathematical Sciences, and the Social Sciences and Humanities Research Council of Canada for the support of this event. This concludes the introduction of the seminar series, and I think it seems I was pretty quick. We might have more time for questions at the end, which I'm very happy with. And on this, we can start now the seminar for today.
Okay, so hello everyone. I'm Sarah Gannon, and it's my privilege to introduce you to today's speakers, Professor Dame Celia Hoyles and Emeritus Professor Richard Noss. So Professor Dame Celia Hoyles is the Chair of Mathematics Education at University College London in the UK. Her research focuses on the design of computer environments to learn mathematics, including developing teachers' mathematical knowledge for teaching using computer activities. She's held positions as the President of the Institute of Mathematics and its Applications, the Director of the National Centre for Excellence in the Teaching of Mathematics, and the Chief Advisor for Mathematics to the UK government. Dr. Hoyles was made a Dame Commander of the Order of the British Empire in 2014 and has been awarded the Royal Society Kavli Education Medal and the International Commission of Mathematics Instruction Hans Freudenthal Medal. Richard Noss is Emeritus Professor at the University College London in UK. His research focuses on the design of constructionist computational environments for learning mathematics. He was a founder of the UCL Knowledge Lab, where he was co-director, of Kaleidoscope, the European Network of Excellence for Technology Enhanced Learning, and the International Journal of Computers for Mathematics Learning. Dr. Noss has also held positions as a Fellow of the Institute of Mathematics and its Applications and the Director of the UK's Technology Enhanced Learning Research Programme. He's received the award of Academician of the Academy of Social Sciences. Together, Dr. Hoyles and Dr. Noss are co-directors of the Scratch Maths project investigating teaching programming to support elementary students' computational and mathematical thinking. So with that, I warmly welcome Celia Hoyles and Richard Noss for their presentation, Mapping a Way Forward for Computing and Mathematics, Reflections on the UCL Scratch Maths project.
Yeah.
Where is it? Show.
Yeah.
Hello. Can you all hear me? Yes? Is that okay?
We can hear you. You will need to start. Yeah, perfect.
Well, I'm Celia Hoyles.
And I'm Richard Noss.
And we have done many presentations together very happily over many years. This is the first one we've done virtually. And I want to thank Chantal and George for giving us this opportunity. It's going to be a learning experience. We will do the best we can for you. I can't say it's completely without stress, but most of life is. I just want everyone to get through it safely and well. And I want to say something to begin with. I will be doing most of the presentation because it is a virtual space, and Richard and I, we didn't quite know how to do it best separately. You know, when you're in a room with other people, we can jump up and down and argue. It's a bit more difficult in this space, as well as Richard hasn't been too well recently. So he decided to leave it mainly to me, and then he would have the right to interrupt when and if he wants to, because he's sitting very close to me.
Oh, I will want to, don't worry.
So he will want to interject if I've forgotten something, and certainly will answer the questions. But what I wanted to say is this presentation is from us both. We just didn't think that doing it together in this particular format would be particularly helpful. So thank you for inviting us. And we are going to really reflect on what we call the UCL Scratch Maths project, which actually finished most of its work some time ago. So it's quite an opportunity to reflect back on what we did achieve and what more we could achieve if we did it all again, or somebody else could do it all again. Because I think the area of computational thinking and mathematical thinking is something that is ripe for research. So our inspiration, us, Richard and I, in the Knowledge Lab, was when we heard that the chief executive of Google, Eric Schmidt, had visited England and said the following: "I was flabbergasted to hear that today computer science is not even taught as standard in schools. In fact, we have what was called an ICT curriculum. And as he said, your IT curriculum focused on teaching how to use software and gives no insight into how it's made." And we thought, goodness, he's so right. We want to know how to use PowerPoint, Word, and other applications. In fact, we all have to use them even more all the time. But really what Richard and I had believed over many years is computing is much more than that, and we should be much more than just using the software, but programming it. There was then in England a report by our Royal Society, which is the highest academic science society in the country. Wonderful people. It was founded by Isaac Newton. And so if you get the backing of them, you usually get things done. And they wrote a report, Shut Down or Restart, in 2012. And that was in a way saying, let's get on and doing not just ICT, doing computing.
Sarah, sorry, Celia, it seems that the screen is black. An attendee just mentioned that. Could someone confirm that it is for everyone the issue that the screen is showing all black? Okay, we get that the screen is fine for lots of people. So sorry for the attendee with the black screen. So let's continue.
Chantal, I'm very glad if you tell me if the screen is black or if I'm black or you can't hear me. We just had to do that. So I think the whole idea behind this Royal Society report and afterwards is that learners, that's students, older learners, should not be slaves of technology, but go to be its master. Not just consumers, but creators. Clearly not everyone can create, but at least see somehow what the technology is doing and why. So following on from that report, there was a lot of pressure, a lot of communities working hard. 2014, I can't believe it's 6 years ago, they brought in a national computing curriculum, and it was statutory. That means it's the law that all schools have to deliver it, have to teach a computing curriculum. I'm sorry to go on a little bit about the rather boring case of England, because every country does a different thing. Our country in England went down this road, rightly or wrongly. We have a statutory national English curriculum, a statutory national maths curriculum, and so we now have a statutory national computing curriculum, where every school has to do follow that curriculum, at least in guidelines anyway. And that's from age 6 to 16. And this is an important context for our research project. And the key aspect of this curriculum, if you look at it, you can find it online, is that pupils should design, build, and debug programs. Everybody should, from age 6 to 16. You think of that potential in terms of how much students will know. And what was set up was the National Centre for Computing Education, and you can find it online. And that was in the result of noticing that okay, we'd love to have a national computing curriculum, but there's a bit of a gap in skills. A lot of teachers won't feel equipped to actually teach this curriculum. So the National Centre was started in 2019, and a lot of money was given to set it up by the government. Actually, compared with the money we spent on COVID, rightly so, I think, that's nothing. But however, at that time, that was a lot of money. And I am honoured to be a member of the academic board of the Computing Centre. So then there was another report by the Royal Society, which talks about after the reboot, which is all about how we must really upskill our teachers in computing. The question that I want to ask you, and we will ask in this reflecting on our project and going forward, is how does programming fit with the rest of the curriculum? In our country, in England, it's in a separate box, computing. That's where programming is done. Other countries in the world have gone down different routes. Some don't have it in the curriculum, in after-school clubs, but I am particularly interested in where programming fits in the maths curriculum. So in a way, every country has to work out its own salvation, depending on how their curriculum is organized. But I think we can still all ask, as researchers, how does programming fit with mathematics? Now, our background, Richard and mine, is we're mathematicians way back, and we're in maths education, and we were inspired by Seymour Papert and the vision of constructionism and the potential of logo programming way back in the 80s. And I still feel inspired by this vision. Okay, there were lots of things that didn't work as well as they could have done. Goodness me, then we had one huge computer in a mainframe in those days, and now everybody has mobiles and laptop computers, and most schools have computer access. And of course we have the web, and so we are a lot further on. But Richard and I are still inspired by that vision. And we were involved in the logo movement, 50 years of research. Many of you, I hope some people who are watching, were part of that research program. There were those big conferences at MIT in the 84 and 85. And then there was the logo maths movement that Richard and I were part of a group who led that. We saw there was potential for mathematics. And why we see this as potential for mathematics, I will talk a little bit later. First of all, constructionism. There are lots of ways that people think about constructionism, but probably, and I still believe, that really when you're making something, building something that's personally or socially meaningful, and you can share it with others, so you can reflect upon it yourself, you can debug a relationship in reaction to feedback, that I think is what constructionism is. So if people just talk, it's very hard to pin them down to argue and discuss and critique. If you build something, and particularly if you build it in a symbolic programming language, everybody can look at it and debug it. It's part of constructionism too, which I think is so important, particularly now maybe, that we should really only be thinking about designing environments for powerful ideas that really give the user some power that they didn't have before. And this should be in well-designed activities. And it should be personally meaningful, and there should be some emotional connection. I think in the early days, I didn't quite give that emphasis that it was due. We also didn't give enough emphasis about the importance of teachers in the past. But we have learned a lot, but the personal, meaningful, the power, the wow, the wonder, and teachers are all important. So going back to maths education, and this is very simplified maths education, one slide I'm going to cover maths education. One of the things that's a real obstacle to thinking mathematically is what I see as separation of procedures from concepts. just knowing how to do things and knowing why you're doing it, in a nutshell. And so much of school maths is about doing stuff, just turning the handle and out comes an answer. But why on earth are we doing it? And isn't that why so many people don't like maths and don't get maths? And so learners actually lack any ownership of the maths. So I think that's an obstacle to thinking maths. They turn off, they don't want to do it. And this is what I think we can do something about with programming. And there is a claim way back, actually, that during interactive learning, that was talking about talking to each other, but even more so when you're interacting with a computer and people and teachers. Students can develop what is called autonomous mathematical habits of mind. That, I think, is a very powerful idea. So autonomous, so they actually take decisions for themselves, and their habits of mind, and they're mathematical. And one of the two that I've been mainly concerned about over many years is that students really feel emboldened and want to conjecture about mathematics relationships, have enough engagement with them to think, I think I know what this is about. This is what I think it is. And also seek explanation and justification. Because so often students don't do that. And that, after all, is a very powerful mathematical habit of mind. And what way back, Al Cuoco, Paul Goldberg and June Mark talked about, they gave some examples of these habits of mind. This is what you do as a mathematician when you're thinking mathematically. You pattern sniff, you visualize, you experiment, you tinker, you conjecture. This is just trying to find out how to solve problems. And so you get away from what Guy Brousseau said, this didactical paradox, where students just guess what's in the mind of the teacher, just get through it, don't really try and engage with the mathematics. So for me, what I really want to do with programming is to link it with thinking mathematically, and that is the awareness and appreciation of mathematical structure, what it's all about, why we are doing it, and help to produce coherent explanations and reasoning. Help together, do it collaboratively, but that is a really important goal in mathematics. And also, very crucially, to be comfortable with the formal expression of relationships, whether it's in algebra or whether it's in a programming language. And that is crucial for thinking mathematically. Now, what we know from so many people's research, we know that above all of those is important for mathematics, but we also know in mathematics, we must bring in the human side, because it alienates so many. Too many are anxious about it and feel they're no good. We have to bring in people, we have to bring in their stories, and their conversations, their games, and their emotions. And this is what I feel we can achieve all of this, maybe a little bit better, with programming. There's other ways as well, but this is what we have tried. Now, what this seminar series is about mathematical thinking and computational thinking. So I've had a short go at mathematical thinking. And now what is computational thinking? Now, way back before our project, we found a definition of computational thinking, and this we slightly tweaked it, but this is basically what it was. Is abstraction. It's very important in computational thinking, seeing a problem and its solution at different levels of detail. Algorithms, crucial to computational thinking, thinking about a task as a series of smaller tasks. Decomposition, understanding that solving a larger problem can involve breaking it down into smaller ones. Pattern recognition, so important in computational thinking, looking at patterns in responses and appreciating that a new problem is very likely to be related to something you've done before. That is such a crucial thing in computing. And generalization, realizing that a solution to a problem can be made in ways that can solve a range of related problems. All of those were in our definition of computational thinking. And all of those, for those of you from mathematics, will see these are very deeply mathematical as well. Slightly different meanings for some of those words that clearly, when you're bringing those two together, you should make explicit. But still, they're still there. So We want to see computational thinking alongside mathematical thinking. They are not the same, there is an overlap. And we, in our UCL Scratch Maths project, we're looking at that overlap. We are concerned with programming. So what does it mean to programming? Going back to what I said right at the beginning, and why program? You build a program to try and understand how something works. Build a program that actually models what that thing is. And it's quite interesting in the time of COVID, we've had so many mathematical models presented to us by our government of whether the pandemic is going up or going down and where, and they're all mathematical models. Now we need to be able to understand those models, how they work. And in understanding, when you're programming, an important part of that is tracing it through, seeing it work step by step, and then seeing if you made a mistake, you debug and you share your answers. So this is crucial. This is at the absolute core of the MIT logo movement, and this is still, I think, at the core of programming. Programming looks different, but it actually has those same core ideas. Now, I dare to say what we know about all those years of research with programming, that goes back a long time, not just in Logo, but in other programming languages. We probably know that there is evidence that through programming, students can explore mathematics in different representations, you know, the visual, the symbolic, and can link them. They can explore geometrical structures, that's more the Logo world, and relationships. And they can look about using variables. Variables in computer science are slightly different from variables in mathematics, but you can use one to support the others, provided you make those differences explicit. But also can help students engage in reasoning and problem solving. And for those of you who might be listening, who are involved in school mathematics, the hardest thing to get students engaged with, particularly students who feel themselves not so good at maths, is to actually go through reasoning and problem solving. And our claim, this was our claim before our project, is that given all that background, is that unless learning to program is carefully designed and managed and sequenced, we have to have good design. It is the advantaged learners who tend to have most to gain. Everybody can gain, but we know from prior studies that they are the ones who might gain the most. So, going right back to the beginning of my talk, I said now we are at a time where we have a new national computer curriculum, which is statutory. Every school in the land in England had to do it. A lot of people were nervous about it. And Richard and I got together and thought, for goodness sake, we must do a project on this. We've been working on programming and mathematics for many years. Let us put in for a research grant to see if we could get some money to devise something. And we were going to use Scratch, which many of you know is a descendant of Logo, and it's a block-based language. So off we went and we put in a project and we won some funding. And what we did, well, first of all we did, I shall introduce them to you, we got together a team of wonderful people to work with us. And although this is Richard and my presentation, the actual what we talk about and what we did is the result of all the people in our team who worked together on this. But we developed a 2-year curriculum, and this is way back. You have to try and remember 2014 and 15, before coding and computing was such a big phenomenon. There wasn't so much about. But we decided we were going to work out a 2-year curriculum with teachers for 9 to 11-year-old students in England. And it would be aligned, that intersection, aligned to the national computing curriculum, statutory, and aligned to the national mathematics curriculum. So we don't going to do all of computing through programming in Scratch. We're not going to do all of maths through programming in Scratch, just those bits that who we felt we were could be regarded as quite expert, thought it was beneficial to do. So we want our Scratch Maths curriculum to support the teaching of carefully designed core ideas in computing program alongside fundamental maths concepts. So we picked the computing concept and we picked the maths concept, and we tried to see how can we devise a curriculum that would support both. And I must acknowledge our funders who generously funded our team for our work. So we supported those, the computing curriculum by using Scratch, and we supported maths learning by picking out some maths and teaching it through programming in Scratch. It's very particular. It's just not any old Scratch. So this is the phases of our project. As those of you who are researchers, you know you often go through these phases. First of all, there was the iterative design. Then there was implementation at scale. And our funders insisted that we had to implement in scale. And we accepted that challenge. In fact, I was quite excited by that. We've all done case studies, but we had to do it across England. Then we had a summative evaluation that I'll talk about later. And we are in this final stage of impact and dissemination. And every stage, to be honest, is quite exciting and brings new challenges. And we are being at the stage of impact and dissemination, talking to you, has given Richard and I a chance to reflect back on what we did before. We can't go back to 2014. It's such a different world in so many ways. But you have to remember that's where we were when we started. So at the iterative design phase, first of all, let me introduce you to the project team. We were a mixture of people in education, computing, and in mathematics, education in particular. And there is us, there's Richard and me, there's Ivan Kallis, who many of you know from Comenius University, Slovakia, who developed one of the very early brilliant logos, who we were lucky enough to get lure to London to work with us for all this time. We had Laura Benton and Piers Saunders, who are our colleagues in UCL Knowledge Lab, and Dave Pratt, who many of you will know in maths education. So a really strong team, but really interdisciplinary. We weren't all maths and we weren't all computing, and so we spent a lot of time arguing or discussing, let's say. So in the iterative design stage, in true iterative design style, we worked with 4 schools. They were in London, and you will see some at the end on our video. And in these schools, we tried all our stuff out. We designed the materials, we argued about them, we thought what were the best materials, we tried them with the schools, we got feedback from the teachers, and a lot of them have done wonderful stuff and are still doing wonderful stuff. But out of that, we knew we had to scale. It'd been lovely to stop there, but we had to scale, and to scale, you've got to have frameworks for scaling out, to share your ideas more broadly. And so we developed an explicit pedagogical framework based on lots of maths education research. We developed an instructional sequence and professional development materials, but the main output was also our curriculum materials. The other things are just as important, but really it's the curriculum materials that everybody looks at. That's why I've got it in red. So what's the pedagogical framework? It was the 5 E's. And it's quite good to have a sort of jargon, because a lot of our teachers took this on, the 5 E's. Explore, envisage. That means think about you do it before you do it on the computer. Explain. Explain what you've done. Try and tell what the reasons about it. Exchange. Collaboration is at the heart of our project. Work together, share, and try and defend your approach. And then the final E, the bridge, which is what we learned from all those years in the past in Logo, is we didn't make, we could see all the links to maths, but so often the links to maths was a bit, let's say, vague for a lot of people. So we think you have to make those links to maths as explicit as possible. So we called it bridge because we couldn't think of the right word beginning with E. So we thought bridge is good enough. So behind all our materials is that framework. I'm not sure how successful it was, but that was there. This is our instructional sequence. It was 2 years. Oh, sorry. So it started for 9 to 10-year-olds. So we had materials for those students. And the main focus of that was computational thinking, or learning a bit about Scratch. So you're getting some of the skills, the instrumentation, as we call it, so that you can start exploring the maths more explicitly the next year in year 6. And you see that arrow along the side, because obviously the students are getting older. They go from year 5 to year 6 in our country. And the idea was that all that experience that they had developed in year 5 and the teachers had developed would be passed on to the next year. We know that the students would be passed on, but we were hoping that the expertise would be passed on to the teachers as well. This is something that we learnt may not always be the case. So we had 2 days of professional development. Had a first day, then they go try things out in school. This is a very standard way of doing professional development. Try them out, support it, set them particular what we call gap tasks, then come back for reflection. I have to note this. This is a very country specific thing. In England, at the end of year 6, that's the end of when they finish their, usually in about June. Actually, it's all been cancelled this year, but in about May, June, all these students take a very high stakes national maths test called Key Stage 2 test. This is high stakes for schools and for students about, you know, where the school's going to be placed in a league table. It is really important, and I'll come back to that later. So the outcome 3 of our design work was all these curriculum materials, about 20 hours focus. And you can see the first module, 3 modules that for in year 5, they were mainly about computing with Scratch. So we're making tiling patterns. We're doing beetle geometry, turtle geometry, for those of you who knew Logo. Then we're talking more about collaborating sprites, which is a really important thing when you're talking about these programming languages. In year 6, the titles of the modules deliberately are much more mathematics. If you read them, you're building with numbers, you're exploring mathematical relationships, you're going to be playing with coordinates and geometry. And so those are the materials, and they're all freely available on the UCL website. And we are very happy for people to use them. They have been used a lot. I hope they'll be used more, but it's nice to know how they're being used. And let me just talk about another outcome of the teacher and support materials. Very detailed they are. Every module has all these activities, this starter project. We did a lot of support, and I must say, well, Ivan Callas, Laura Benton, Piers Saunders all did an enormous amount of work doing all these things. We had unplugged worksheets, very important for bridging from the world of maths to the world, from the world of computing. Discussion points. We did have end of module assessments too that we left the teachers to try. PowerPoint presentations, you can see they're there. So try and help. We have to remember that this was so new for teachers. Now, 6 years later, they won't need quite so much support because so many are much more familiar with Scratch and the ongoing work. So, but from the start, it's blended learning, and that I think people now say is crucial for the success of computing, on and off the computer, and different modes of classroom interaction. Just a word about the modules. It's a glimpse of one of our modules, beetle geometry. It comprises different investigations. It has an introduction where we try, you can't read it all now, but we tried to make cross-curriculum links. But this was important for us. It's the key vocabulary and the concepts in this module 2. The maths curriculum, so making a link to the statutory maths curriculum, making a link to the computing curriculum, made very clear at the bottom. This is not to say that everybody made those links, but at least we tried to make those links to support others to do it. The computer tools, Scratch Maths looks different from Scratch. First of all, the tools look different. Those of you who know Scratch, when you open up, you get this cat. When you open up Scratch Maths, you don't get a cat. You get, if you open up module 1, it's about tiling patterns and you get tiles. If you open up module 2, it's beetle geometry and you get a beetle. Now there is a difference between our tools and the cat. Underlying, it's all Scratch. We are trying to exploit all the potentiality of Scratch. But what we deliberately did in those modules, for example, is we brought back direction. Because when you're looking at that cat, at least I could, never quite sure which way he's going. But with the beetle and with the tile, you know exactly. And so because we wanted the mathematical geometrical affordance, we wanted to be able to see about heading as well as being able to move. We were asked by the organisers to maybe think about exemplary or favourite tasks. And this is the task that Richard and I find, I must just see what the time is, exemplary. And this is called polygon fireworks. And why we like it, I was going to demonstrate it. It's a casualty of the virtual world, is I just couldn't risk doing it in Scratch. Sorry, but you can all imagine it. That is a view. If you came to our home in London, we live in Primrose Hill, that is a view of Primrose Hill. So it's got some sort of our personal identity. And we have times when we celebrate with fireworks, and you can see them from the top of our hill. Not so often recently. But what you can see, our fireworks are polygon fireworks. They're different sizes, they're different shapes. They could have a noise if you wanted. But what we set this as a project, it has our own narrative there. It is deeply mathematical to actually do that in terms of not only setting up all those polygons, but also positioning them so that they're in the sky and not in the ground, because fireworks, as you know. And I just want to briefly look at the programs. You always have a starting up program in Scratch, and you can see you immediately have got something about coordinates. Go to X is 0, Y is 0. Definition of a polygon. This has got a variable, which we have named as number of sides. You've got side length, you've got the number of sides, you've got the 360 total turtle trip. Then for the firework display, the thing that you have to do, obviously in programming, there are little technical bits you have to get right. And I've just picked out the main ones. But in order to do the fireworks display, what you have to do is that the program on the right is jumped around in the sky. So you have to put your pen up because you don't want to be drawing anything. And then you jump to coordinates where you're in the sky and not in the ground. So you are doing something about coordinates. You are doing something about polygons. You are setting variables. Here we've got the number of polygons, the number of sides of the polygon, and the side length. And this is our program. So I want to go on because the next thing very related to that is our unplugged. I think unplugged is really important. And I think I don't think I have time to go through these, but if you just take a few of those programs and trace them through and visualize what the outcome will be, this is a very mathematical task. What if you set the side length to 30, you then you've got a little program doing square, and then you repeat 8, change the side length by 10, and then you do square. Visualize what that does. What was the side length at the beginning? What was the side length at the end? And there are 3 programs that look terribly similar, but do they get the same output or not? This is a sort of exercise for you to think about. Let me move to the implementation. This is all, most of our effort in the first 2 years was on design work. And this is now we're moving out to scale. We're moving out across England. It's quite a big country when it comes, very different. And we have 7 regional hubs and each with a hub lead. Just want to mention, you might have noticed there's only 6 dots on that picture of England. This is because 2 of the hubs were in London, one north of London and one south of London, because London's a big place. And we had more than 100 schools. That was our challenge, to go out everywhere and to recruit these crucial people, these hub leads across the country. That's the numbers, big numbers we did. 110 English primary schools. We had to recruit them. They had to join. To be honest, they wanted to join, hopefully because they liked our program, they liked us, they liked our team, but also they wanted help with computing. There's no doubt about that. So there was professional development in each region, led by one of us in the team and the hub lead. So we spent a lot of the time whirling around the country, learning a lot about the differences across the different parts of our country, which is very interesting. And an independent evaluator, this is our funder, insisted happen, was appointed in 2015. And I just want to pause because that's taken me one slide to do. That took us an enormous amount of work to set up, to recruit the leads, to make sure the leads understood our program or aligned with it and we could work together, to recruit the schools, to organize the professional development. All of that is a big deal, actually. And when you say scaling, it's a matter of getting the numbers. We got the numbers, and I understand why our evaluators wanted us to get not just everybody who knew the Scratch Maths team in London, completely randomly, but it is a big deal. So moving on to summative evaluation. Now we move to the end of our project. They've implemented the materials. There was such a business now of thinking back of it. Do you remember where you're in an area, some of the schools are doing our project, some of the schools are not doing it. The schools who are doing our project were not allowed to share with the ones who weren't, because that's leakage. So how would you ever know there's going to be any difference? So there are lots of problems with this model that we are very happy to discuss. But we went along with it. We were going to go for it. But I think that there are quite some worries about that. But so here we're going, this is in the final stages. So how is it going? We did lots of surveys and interviews, online interviews with the teachers. And we wanted to find out about the fidelity of our project. What was the fidelity? That is a very important word in implementation science. How far was the project delivered in the way that we wanted it to be delivered? Did the teachers do the professional development? Was the technology there so they could do it? Did they cover the curriculum? Did they actually do it? And did they follow the sequence? These are important ideas if you're looking at whether your initiative has worked. And the independent evaluator, their job was not to look about fidelity, really. They really wanted to look at student outcomes. Did the students do better having done our program? So they did a randomized controlled trial, which is the gold standard at that time. And so the schools are over 111 schools were split in two. Of course, they don't split in two, so one got lost. I never knew quite where that went. We split into two. Half were given our treatment. The other half were in the control and would do the treatment the next year without any leakage between the two. And they were matched, the two groups, on the basis of socioeconomic status and prior attainment at 8 years old. Very small matching measures, actually, but because there's so many other things that we could have said they should have been matched on. But then the outcomes, one was the computational thinking test score. Our evaluators devised a computational thinking test. And at the end of year 6, the National Key Stage 2 Maths, which everybody takes, very high status, as I said. So here are the findings from the evaluators. There was a positive and significant impact in favor of Scratch Maths on computational thinking scores. This was particularly evident among socially disadvantaged pupils. That's those who have free school meals. There was no difference between girls and boys. If you read the executive summary of the evaluators, that's not at the top. But I don't think they realize, like we do, that actually making sure girls do as well as boys in this area of computing and maths is rather important. There was no evidence of impact on the National Key Stage 2 maths scores. So that is the result of the outcome measures for students in a nutshell. They also said, I've just picked this out from the report of our evaluators, that Scratch Maths is an affordable way to cover aspects of the computing curriculum in maths lessons without any adverse effect on core maths outcomes. Now, when you read that, you think, oh God, that's not very exciting. But the more I read it, the more I live with it, I think it's rather important, because maths, at least in my country, is so high stakes. If anything is thought to take away from maths, then they won't do it. So this was quite important to say it might even be advantage for you. These evaluation reports, everything's there are available. So we've got articles, some by teachers. I've got all these references, but you can have my PowerPoint and you can read this. I want to say, why are these findings? These are the findings again. Why is there a positive and significant impact on Year 5 computational score? Why is it particularly evident amongst the disadvantaged, and especially for girls? Why was there no evidence of impact on key stage 2? Now, the point is, we don't really know, because we did design research, we went running around, we did interviews, but we don't really have any hard data on implementation science about answering those why. We do know some things. We know that the fidelity for professional development and curriculum coverage and teaching was very high in the first year. Everybody did scratch maths and did it well. And there was a dramatic drop in the second year. And that was probably the negative impact of the high stakes maths test. In fact, I said probably, I know it was. A lot of the schools just didn't do much scratch maths because they were too busy revising for their key stage tests. So we also do know there was huge variation in pedagogy across the country because computing was new and maths is sometimes a bit scary. They're what we called lethal mutations. There was us with all our E's and our, explore and all that, and listen to the children and share. And we saw some things that were nothing like that whatsoever. And so it's not surprising, perhaps it didn't achieve its aims. And I also think we should return later. It's too quick to evaluate such a big project with so many new things like in computing, and some of the maths ideas are really quite hard. So I think actually I found recently in implementation science this quote: effective implementation is likely to take 2 to 4 years before initiatives are fully embedded in everyday practice. So we should really come back, let it all go away and leave it, and then come back in 4 years' time. And actually, we've had the chance to do that in some of our schools, and you can see how some of those teachers some of them were quite nervous of it, and now it's all just bread and butter to them. So now moving to our final step, impact and dissemination, which is really probably, well, no, every stage of this project is interesting and exciting, but we're now about what's happening. Have other people using our materials, doing it differently, and why, and what are they doing? And just briefly, we have upgraded the materials to Scratch 3. Scratch Maths has gone to Australia, and actually Richard and I were lucky to go there too before the lockdown, and we had a wonderful time, courtesy of Elena Prieto Rodriguez and Catherine Holmes. And they're doing Scratch Maths differently, but wonderful stuff. Scratch Maths went to China, and we heard from a couple of Chinese researchers who were implementing the material, doing it, looking in rather different environment to us lying around on the primary school floor, but never mind, they were doing it. And more recently, Scratch Maths has went to Spain, and the Spanish Ministry of Education translated everything into Spanish and updated the materials before we did it in Spanish, and implemented all the online teacher training and did it, and evaluated not by RCT, but pre and post tests. And this is what they said. Well, this is what Google Translate says they said in their report, because I'm afraid I don't really read Spanish well. But this is what they said. The results show that it's possible to include programming activities in 5th grade in mathematics, so that students not only learn to programming and engage in computational thinking and improve the development of their maths competence greater than their colleagues who have worked in the same area using other types of activities. So they got a result rather similar to ours. The others were doing stuff in computing and in maths, but it gave them an edge doing this together. Some personal thoughts on the limitation of our project. Now, from the hindsight, at several years on, I'm very much hoping that other people will do a better job upgrading and doing it in their own countries. I think the assessment just by key stage test was crazy, actually. Not only is it at very high stakes, but it also doesn't really relate to the mathematics they were learning in our modules. We need much more fine-tuned and nuanced quantitative measures. If you remember, these were our modules. We did do assessments at the end of our modules. We should have, well, we didn't have the time. It would be lovely to make more rigorous end of module maths assessments and computing assessments. The assessment of teacher outcomes, I wish we knew more about the teachers' feelings about the computational concepts that underpin what they were doing, like parallel processing and receiving messages and sending messages. What was their competence and confidence at using programming? We didn't do any of that. As I said before, we have very little to say about what actually happened in the classrooms, because that's really what will explain the results, some of our rather good results about fidelity, and what about those gender interactions, and why was it that the socially disadvantaged did better? We have our ideas, clearly, but we don't really know. I do think one of the things where fidelity fell a lot in year 6, and always falls a lot in terms of teaching and learning mathematics in schools, is professional development. In the first year, everybody did it. Everybody did it, found out about it, spread it amongst their schools. In the second year, far fewer. It's the first thing that goes, and we do need a commitment to it, because after all, if you're a bit nervous about the maths and you're a bit nervous about the computing, it's very difficult to teach scratch maths along with the ease. So I would like to say, being a little dictator here, that you can only teach it if you've done the professional development, but that's of course impossible. So these are my general reflections. I think I've got to stop. I think we have a lot to learn about this in terms of teachers, pedagogy, confidence. I know there's issues about transition, what happens after. I know our colleague Ivan Callas is thinking a lot about transitions from the younger ones to come up to scratch maths and then going on to the next. What an excitement we could have. There is, actually you've got to get the schools to support us. So we need more research on implementation with these different foci at scale, and I'm not quite sure how to do it unless you had a massive team. So if I'm allowed, I'd like to just show a video of our project. I think I've just about got time. But Chantal's saying yes, so I will. Now this video was done by our two wonderful colleagues, Laura Benton and Piers Saunders, in 2 of our London schools. The data is out of date because it's done way back many years ago. But I just want you to see the essence of our projects and watch the kids and what they do. So I think it's a great chance for maths and computing to bring them together. And as one of the students in our project says, it's like magic in front of my eyes. And let's hope this works. Scratch maths is a big funded, it's going to go for a long period of time, and it's trying to make links between programming and mathematics.
We are working with schools in different ways. We have a small group of schools where the teachers are really deeply committed to helping us to develop the curriculum. And we have a much larger group of schools where we actually try things out and do the actual research.
But for us, Scratch is a breath of fresh air because it allows us to approach the teaching of mathematics in a new, exciting and engaging way.
I like it that you can have algorithms and you use maths while on a computer. I like when you've just made a complete script and it finally just works.
What we really like about Scratch is when you press that start button and you see your script come into action. It's like magic in front of your eyes, and I really enjoy that bit.
So how we work in the design process, a group of us who have had some experience, that includes teachers but academics, we worked together and we thought what would be the best materials that we could develop. What are the big ideas in computing? And then what are the crucial ideas in mathematics?
So what we've spent a lot of time doing is building a new mathematics curriculum that people can express themselves in Scratch rather than in algebraic notation?
Because it's a non-written form of maths. It kind of accesses all the children, so it allows, as a teacher, you to focus on children that maybe aren't so confident in writing and written maths.
Often when you're looking at angles and degrees, you're on paper and the children don't necessarily understand that's a physical turn, and getting the children to act out actually doing it physically and turn themselves, it meant they were seeing those degrees in a different way.
The Scratch Maths has been invaluable in my knowledge and understanding and confidence in teaching computing, because it's brought everything to do with teaching coding back to the basics and built it up.
I use the PowerPoints in each lesson. They're really straightforward and they do follow the teaching pattern that I want to follow.
The materials are really easy to understand. There's vocabulary, there's all the plans already made.
You get children who finish quickly. It's really good, you can move them on. And for children who are struggling a bit, there's lots of visual and lots of unplugged activities as well, which really help.
It's not just about being able to debug or understanding the language of, say, Scratch Maths, but actually getting the children interested in maths so that we can raise standards in maths.
Already the project is fully embedded in our curriculum. It's also providing the tools to give the teachers the knowledge, skills and understanding to deliver the programme with confidence. This is a resource which will raise the confidence levels of your staff, of your pupils, indeed of the whole school.
I don't know how.
Press escape.
It's press escape. Right.
Okay.
Yeah. I just want to say we're both in love with that head teacher at the end. He's one of the best head teachers I know, and he is so committed to our project. So thank you very much. I shall look forward to the questions.
Celia and Richard, thank you so much for your presentation, taking us a tour through the project and seeing the whole of it all at once. And also thank you so much for your kindness and your patience. Chantal and I spent a lot of time with you prior to this, trying to set all of this up, and you've been wonderful, and we really appreciate that. You give so much of your time for projects like this. Really, thank you. So it is time to open it up to some questions, and first we'll open it up to anyone that's in the panel today. So we have a couple of, so we have Krista raising her hand. So Krista, if you could turn on your mic and ask your question or comment.
Hi, Celia and Richard. Thank you so much for your presentation. You're my heroes. One of the measures of impact that is not part of your study is that I'm going to be using your curriculum in my undergraduate STEM education course for pre-service teachers this fall. So with COVID, we've had to switch from hands-on robotics to, Scratch. So I'm quite excited. I'm just kind of curious a little bit about the context in England. Does the government provide computers for every student so they can participate in this computational thinking or computing curriculum?
More or less.
Yeah, more or less.
Yeah.
Every student in the land has a computer. Actually, they're slightly different configurations, but actually one of the fidelity measures was technology accident. If you mentioned, I didn't really mention it, I should have done, it was on my list, but that was not an issue in our project. Everybody had access, different sorts, laptops mainly. Some schools, they still had computer labs, even in primary school, but on the whole, they have them. And actually, I must just say, our team has been working because of COVID, I suppose, but also other things to try and move it so people can use it at home. And as far as we can tell, most homes, I mean, not in all homes, most homes will have access to laptops. And if not, in this time, schools will provide them with laptops for home.
Yeah,
so I think,
and the system doesn't make many demands on the computer. I mean, a Chromebook and a just about any browser will work fine. So even if the kids were buying their own computers, it would only be a minimal amount.
Well, that's an advantage. We don't have the same access here, which with COVID has really left some of our disadvantaged children even more of a disadvantage. And which brings me to my next question. What are your ideas about why disadvantaged students did better with your program?
Well, I'll start, and this is speculation, because as I say, we don't know. We do know that was a result of the quantitative evaluation, and one that we are very happy with indeed, because as you know, I'm sure in the past computer stuff, it was always the boys and the brightest took over. I would hope that it was something to do with our work. We're very keen, it was very carefully sequenced. It was very almost drummed in that you go from direct drive, you don't jump in. And I think in a way it was the idea, you try and bring everybody, the whole culture of Scratch Maths was everybody's doing it together. And so I would think it was a tribute to the teachers who, you know, really bought into that message that we are not going to let a few kids dominate, because obviously that's always a danger. We are not, and it's not that they stopped them, it's just they encouraged others to come forward. In fact, we saw some. Do you remember when we went to that North England school?
Yeah, and the teacher said, whispered to us, she's no good. She's no good at maths, she said, pointing at this girl, who later on in the lesson ended up explaining to the rest of the class how it worked. So actually, the truth is, we don't know the answer to your question, but it's something to do with kids who previously felt excluded from that type of learning, for formal reasoning, finding that there was a way in for them personally.
And I do think it's challenging preconceptions. I think we all suffer from preconceptions. And then you'll find somehow in this sort of environment that kids who didn't flourish and excel do. And you just got to allow them to. And I think that's what our whole curriculum was. Do it slowly, share it, and just celebrate the joy of some of the things that they can do. There is something, because many more kids are very, very, very proficient at Scratch. And they want to do things whirling about all over the place. And you somehow have to damp that down a bit, because you don't want just to have a wonderful effect. You want to know this whole thing, why did it happen? What would have happened if I changed it slightly? That sort of thing. So we don't know. You could find out for us.
Yeah.
Well, it's been my experience as well too. You know, children who've been deemed to have no number sense are phenomenal programmers, and it shows up later in their math as having that number sense too. But I mean, I could talk to you for hours, so I will mute my mic and let somebody else have a chance.
Looking again at the panelists, I don't see any hands up for now, so we will continue with the attendees. I see Abdul Karim. I will allow you now to talk. If you want to unmute your microphone, please, to ask your question.
Okay, hello. Okay, thanks for your presentation. Okay, my question is this one. Okay, if I understand the meaning of the presentation, you are talking about primary school, level 5 and level 6. So I just want to know if it's only this level in UK, you just use this level, you just do the presentation for Scratch Maths in these levels, or after this primary school, like secondary school, if the students are at secondary school, sometimes when they have problems in mathematics, they leave some programs as primary school, and if there is no repetition, so sometimes they can forget some skills. Thank you.
Well, if I understand right, the question is whether we restricted the study to students only in those 2 years, and the answer is yes. If the question is why did we choose only those 2 years and not any other, the answer is because you can't do everything. We would love to see a long-term study with kids entering primary schools and seeing how they do right the way through school. Okay. But nobody's going to fund a project like that. Not now, anyway.
But our colleague, Ivan Callas, this is his dream as a computer scientist. His dream is to do exactly that. And so maybe we all have to follow our dreams and... but I'm afraid we focused on those, and whether that was the right decision given our national testing. Sorry.
Okay, thank you. Thank you.
Thank you. I see Gregor Milichik having a question.
Great to see that how it is possible actually to combine computational thinking and mathematics, and that one doesn't suffer for the other. I got a question regarding the professional development of the teachers. How, and if you did so, how did you actually support the teachers during their development, or how should they continue to learn how to use Scratch and programming?
I can tell you what we did. I don't think it was perfect, by a long way. What we did was in each of our regions, we did these 2 days of professional development. So everybody who was going to do our project came to a site, and we had face-to-face, hands-on professional development where we went, some of our team went, Rich and I sometimes went, sometimes the others, spend a lot of time moving around the country. And also our hub lead, who was crucial. The model was the hub lead as well. And we did some of the activities. We talked about the pedagogic framework. We tried things out. We established an online community, and then off we went. And then they tried things in schools, and then we came a few months later exactly and saw them again. And the hub lead, who was a local person or a regional person, kept in touch with them and gave them support if and when they needed. As it happened, the hub leads were mainly computing people. I don't know quite how this happened. We worked with professional associations to help us recruit them, and they were wonderful. But on the whole, they were computing people, not maths people, because the maths people were too busy supporting the statutory maths curriculum, which is so high stakes. So I think there was one hub where we had maths and computing together. But that's how it worked on the whole. You had a hub lead, and then we used to do online advisory as well. But that, to be honest, was not as successful as we had hoped. Maybe after COVID, people would do much more online. Then on the whole, the teachers weren't doing much online. So on the whole, you did the face-to-face, and that was it. Does that answer your question?
Yes, it does. Thank you very much.
Okay, we have a next question by Priscilla Correa. You had mentioned it in the text as a chat. Unlocking your microphone if you prefer to say it out loud yourself. We cannot hear it, so maybe I will read the question to Celia and Richard. Would you say that Scratch is appropriate to explore programming in all grades till grade 12? Or would you recommend the use of different software options as well?
That's a good question. All you can have from us is our opinion, not our results of research. Personally, I think there would be far more scope for Scratch to be taught higher up the schools, at least for an extra 2 or 3 years. But the way that things are moving, it looks to me as if we're going to start with Scratch, and then it'll be seen as a progression to something like Python. And in a way, that's understandable. It's good that Python is a language that everybody uses around the world and so on. In a way, it's a shame, because I can guarantee to you that the world will be full of teachers who say, my kids are nearly ready for Python, when they still have a huge amount they could discover about maths with Scratch. But that happened with Logo, so...
Yeah. I think Scratch is tended to be regarded as something for little children, which it is. It's very good for little children, but I think there is this transition, how we move on to Python. I think a lot more work needs to be done that hopefully you will do.
Thank you. We have Polino Preciado, who has the next question. Please go ahead.
Hello, thank you for the presentations. Can you hear me?
Yes.
Okay, thank you very much. So I wanted to do two things. One is, in the presentation, there was the question about how coding looks in different countries. So that here in Canada, it depends on the province.
Oh, wow.
But in Alberta, there was a commitment to include computational thinking in the curriculum. They wanted to put it to mathematics, but we have the trouble that it didn't happen. It was kind of a curriculum review that hasn't been implemented. But for the early grade levels, the first few years was about following instructions, and that was what the experts in computational thinking suggested, and I saw that as a waste of the potential of mathematics because it was separated from mathematics. That was just a comment of where things were going to, and but then I would didn't change. That was just a comment regarding what it looks like here in Canada or in Alberta, more specifically. My question is the following: I've been exploring kind of the opposite direction. I've seen that we use computation to teach mathematics. So I was thinking more in terms of, computation to teach mathematics, and mathematics that could be applied to computation at different grade levels. Part of that, what I noticed with some teachers in a graduate course is that there's kind of a new math or math which is not in the curriculum, but could be highly useful for programming. And I've been looking, for example, the idea of implementing or teaching more about, for example, vectors in high school that you can use to program video games. And that's a language to go into program for create video games. And this idea, I think the idea of vector could start from early grade levels. So my question is, have you identified mathematics which are not part of the curriculum, but are actually relevant for computer for computational thinking or computer graphics that maybe we may start thinking about changing the math curriculum?
Well, that's a fantastic question, because I think what you're really asking is, can the mathematics that we've traditionally taught for about 100 years remain invariant in schools under the transformation of the computer? And the answer is, who knows? Schools are fantastically good at resisting change. School systems are very good at resisting change in curriculum. So is there a new subject which we don't have a name for, computational mathematics, mathematical computation, whatever? Is there a scope for such a subject to give us the chance to rethink what counts as mathematics? Yes. Do I really believe that this is what's going to happen in the world?
Don't say no.
I won't say no.
I'm sure it's people like you, everybody, we could think of things that are much more relevant now because you let them in.
Yeah.
Sorry, the doorbell's rung. I don't quite know why, but we probably have all these deliveries. It's probably one of them. What we were saying, I just think can we rethink the curriculum? But trouble is, our maths curriculum is often it takes a long time to catch up. But maybe if we all work together, you could set up a commission, make some recommendations. I think now is the chance.
Maybe we will, if that's okay, Celia, we'll have one last question. Unfortunately, there are more in the chat, but I could not go through everyone. The last question from Sohela Hamadi from Canada. She says, I would be thankful to know how do you think about integrating this programming to pre-service teacher education programs?
Well, I want to say, Chantal, you should know more about that than me. But I honestly think, I mean, actually, every move is challenging. I'm not talking about COVID. Every move is challenging. But I think it would be really good to have a group of us, and we would happily join and help if we were wanted, to try and think how you could put it into initial teacher training and programs, because in a way, there's a bit of time to reflect. And I mean, we should be able to do it in England because we have computing and maths a national curriculum, so they have to be in some ways for it. But I think there's a lot to be done on that, and we didn't do that at all. I mean, I think the next step would be how can we get it into teacher formation? Yes, let's do it. Don't you? And I think I'm going to vote for Chantal to lead the way.
Okay, thank you, Celia. If that's okay, I will take over sharing the screen with the last slide. If you can bear with me for a second. Let me see, I'm trying to share this.
You must make sure we come to the next one.
And this. Can you see my slide?
Yes.
Yeah.
Yes, okay. Well, thank you again, Celia Hoyles and Richard Noss, for your insightful presentation and your generosity in answering all of these questions at the end. On behalf of George, Ariel, and Sarah, I would like to thank everyone for attending this first seminar. If you could please take 2 minutes to fill the brief attendance survey. You have the URL here at tiny.cc/OSS, all in capital, -1. It's just for funding purposes. We'd like to keep track a bit of the attendance. You can find you will be able to find today's recording and details for the upcoming seminars all on the Mathematics Knowledge Network website. You had received the link for this. And again, let us thank Mathematics Knowledge Network, hosted at the Fields Institute, as well as the Social Sciences and Humanities Research Council of Canada for the support to host this event. We do look forward to seeing you, having you with us in 2 weeks' time on Friday, July 3rd. Krista Francis and Brent Davis from University of Calgary, Canada, will be discussing computational thinking and experiences in, I cannot see right now, in arithmetic. Can someone finish my sentence?
Computational thinking and experiences of arithmetic concepts.
Oh, that was the concepts I was missing. Thank you. Thank you, everyone, and goodbye.
Goodbye.
Thank you. Thank you.
Thank you.